First, what is rate? The mean rate of reaction is the change in amount or concentration of a reactant or product per unit time. Formula you must know. Mean rate equals change in amount or concentration divided by change in time. Units are grams per second, or moles per second, or moles per decimeter cubed per second. Two quick examples. If a reactant goes from 0.80 to 0.20 moles per cubic decimeter in 60 seconds, that's 0.80 minus 0.20 over 60, which is 0.60 over 60 equals 0.010 moles per cubic decimeter per second. If mass goes from 0 to 2.5 grams in 50 seconds, that's 2.5 over 50 equals 0.050 grams per second. Required practical, we measure rates by measuring gas volume over time with a gas syringe, mass loss over time on a balance, or color change with a colorimeter. On a graph of gas volume versus time, the gradient is the rate. Steep gradient means fast rate. The rate decreases as the reaction goes on, and when it plateaus, the reaction has finished. Key idea for the whole topic. Anything that causes more successful collisions per second will increase the rate. 1. Temperature. Increased temperature increases kinetic energy. Particles move faster, more frequent collisions, and more importantly, more particles have energy greater than the activation energy, so more successful collisions. 2. Concentration in solutions. Higher concentration means more particles in the same volume, closer together, collide more often, more successful collisions. 3. Pressure for gases. Increasing pressure decreases the volume. Gas particles forced closer together collide more often. Rate increases. Same number of particles, smaller volume at higher pressure. 4. Surface area for solids. Increasing surface area means more particles are exposed, more places for reactions to happen, more successful collisions. Large chunks equals small surface area equals slower rate. Powder equals large surface area equals faster rate. 5. Catalysts. Catalysts provide an alternative pathway with a lower activation energy. More particles have enough energy to react, so more successful collisions. Catalyst is not used up. Summary table. Increase temperature, concentration, pressure, surface area, or add a catalyst. All increase rate. Collision theory. For a reaction to occur, particles must collide. But not all collisions are successful. A successful collision is if particles have enough energy and collide with the correct orientation. Unsuccessful, not enough energy or wrong orientation, no reaction. Successful and enough energy and correct orientation, reaction occurs with that little star burst. Key idea. Increasing rate increases number of successful collisions per second. Activation energy, EA, is the minimum amount of energy particles must have to react. On a reaction profile diagram, it's the energy needed to reach the top of the barrier, shown by the vertical arrow from reactants to the peak. Energy profiles. Exothermic reaction. Products are lower energy than reactants. Energy is released. Endothermic as products are higher energy. Energy is absorbed. Factors that affect EA. Anything that lowers EA increases rate. Example, catalysts. They lower EA by providing an alternative route. On the graph, the curve with catalyst is lower. Other factors don't lower EA. They just give more particles enough energy, like temperature, or cause more collisions, like concentration, pressure, and surface area. A reversible reaction is one where the products can react together to reform the reactants, shown with a double arrow. Key features. It can go forward and reverse. Happens in a closed system where no substances can enter or leave. Only energy can be exchanged. Examples you need to know. Ammonia synthesis N2 plus 3, H2 reversible 2NH3. Hydrated copper sulfate CuSO4 plus 5, H2O reversible CuSO 4.5, H2O. Esterification and thermal decomposition of calcium carbonate. The dynamic nature. At the start, only reactants present, only forward reaction occurs. As products build up, reverse reaction starts. Eventually, both reactions occur at the same rate. This is called dynamic equilibrium. In dynamic equilibrium, forward rate equals reverse rate. No change in amounts of reactants and products. The system is not stopped. Both reactions continue. The equilibrium is dynamic. Remember trap. Equilibrium does not mean the reaction has stopped. It means rates are equal. Graph, forward rate starts high and decreases. Reverse rate starts at 0 and increases until they meet and flatten. That's equilibrium reached. Le Chatelier's principle. Definition: if a condition is changed, equilibrium shifts to counteract the change. The system responds to minimize the change and restore equilibrium. Conditions that affect equilibrium: concentration, pressure for gases only, and temperature. Catalyst does not affect position. Change in concentration. Add reactant, shifts right. Remove reactant, shifts left. Add product, shifts left. Remove product, shifts right. System tries to remove the added or replace the removed. Change in pressure, gases only. Increased pressure shifts to side with fewer moles of gas. Decreased pressure shifts to side with more moles of gas. Example N, 2 plus 3, H2 reversible 2, NH3. That's 4 moles gas to 2 moles gas. So higher pressure shifts right toward 2NH3. Lower pressure shifts left toward N2 plus 3, H2. Change in temperature. Endothermic absorbs heat. Exothermic releases heat. Increased temperature favors endothermic direction. Decreased temperature favors exothermic direction. System absorbs heat to counteract increase. Releases heat to counteract decrease. Rate versus time graph when disturbed. You see the rate split when condition changed, then become equal again at a new equilibrium. Effect of catalyst. No effect on position of equilibrium. Only speeds up reaching equilibrium. Same effect on forward and reverse rate. Yield is amount of product at equilibrium unchanged. Example linking to Haber. High pressure favors NH3. Low temperature favors yield but slows rate. So compromise 450 degrees, 200 atmospheres. Removing NH3 shifts equilibrium right to make more. What is the Haber process? Industrial process to make ammonia from nitrogen and hydrogen. It's a reversible reaction. Equation: N2 gas plus 3H, 2 gas reversible 2 NH, 3 gas. Forward reaction is exothermic, releases heat. Conditions: temperature around 450 degrees Celsius. Pressure around 200 atmospheres. Catalyst: iron filings. Yield about 10 to 15% per pass. Recycled to 97% overall. It's a closed system. Reactants recycled. Products removed. Raw materials: nitrogen from fractional distillation of air. Air is 78% N2, 21% O2. Hydrogen from natural gas plus steam. CH4 plus H2O goes to CO plus 3H2. This is steam reforming or cracking. Compromise conditions explained. This is the 6 marker. Pressure: high pressure gives higher yield because 4 moles to 2 moles, but expensive equipment and safety risk. So 200 atmospheres is the compromise. Temperature: low temperature gives higher yield because exothermic but rate very slow. High temp gives fast rate but low yield, so 450 degrees is compromise. Catalyst iron speeds up rate, reaches equilibrium faster, no effect on yield. Le Chatelier link. Increased pressure shifts right, decreased temperature shifts right. Remove NH3 as made shifts right to replace it. Uses of ammonia, making fertilizers like ammonium nitrate and NPK fertilizers, nitric acid production, important for food security and higher crop yields. Reactor and recycle loop. Unreacted N2 and H2 recycled, liquid NH3 collected in condenser/separator. Remember, catalyst does not increase yield. It's an economic compromise between rate, yield, cost. Finally, NPK fertilizers. What are they? Fertilizers containing nitrogen, phosphorus, potassium compounds, provide nutrients for plant growth, replace essential elements used by previous crops. NPK numbers mean percentages of N, P2O5, K2O. So 20-10-10 means 20% N, 10% P2O5, 10% K2O. What each does: nitrogen, needed for proteins, growth, green leaves. Deficiency is yellowing leaves, stunted growth. Phosphorus, needed for root growth, early growth, seeds. Deficiency, poor roots, purple or red leaves, delayed maturity. Potassium, needed for flowers and fruit, disease resistance. Deficiency, brown leaf edges, weak stems, poor fruit. How NPK are made: lab and industrial neutralization reactions. General equation: acid plus base goes to salt plus water. Acid plus alkali goes to ammonium salt. Specific examples: ammonia plus nitric acid goes to ammonium nitrate. That's your N source. Ammonia plus phosphoric acid goes to ammonium phosphate, P source. Potassium chloride mined from rock goes to KCl, K source. Other examples: potassium nitrate, KNO3, potassium sulfate, K2SO4. How to calculate NPK from formula. Work out percent mass of N, P2O5, K2O in compound. NPK ratio equals percent N colon percent P2O5 colon percent K2O. Industrial blending of salts to achieve required NPK ratio for specific crops. Uses and importance: increase crop yield, improve plant growth, essential for food security to feed growing population, supports fast growth for agriculture. Environmental issues: eutrophication if runoff into rivers and lakes. Algae grow rapidly, called algal bloom, blocks light, oxygen depletion, fish die, fish death. Cost: mining potassium and phosphate rock is finite resource. Soil pH issues: leaching of nitrates into water. Need to use correct amount. Overuse causes pollution.